So in this problem, we have the two guys carrying the refrigerator, right? And the refrigerator is not uniform. So unlike some of the other ones we've been doing, it's not uniform in this case. The front of it is heavier than the back of it. So this would shift the center of mass from the center offset a little bit towards the front. Okay, so that's how kind of your picture should look. And actually, if you want like some steps how to solve these problems, if you're one of those people that likes to know the steps, so number one, you should really like draw a picture. It would be very difficult to solve these problems without a picture. Number two, you're going to go ahead and do your FBD. And these FBDs are a little bit more detailed than what we did way back in chapter 3, in that you want to include the location of the forces. So where you place them on it is important for the torque calculations. And then step 3 is where you're going to do your summations, where you're looking for your equilibrium, you're looking for your balance. And there's typically 3 possible summations: your sum of x, your sum of y, and your torque. So those are kind of the 3 summations that you could do. Now you don't always have to do them. Sometimes you can get what you need from doing one of them, and sometimes one of them doesn't even exist. Like in this problem, there is no sum of x, right? And then number 4, you'll just go ahead and then start solving. Sometimes you'll have like 2 unknowns, right? But you'll have 2 equations. I mean, you have 3 possible equations oftentimes, so you could have 3 unknowns, and then you have to just solve for systems. Oftentimes you don't have to go that far though, like this one. Okay, so here's my picture. Let's go ahead and do our FBD. So this time we have the force of this, the weight of this is pulling down here, right, 1 meter away, and they gave this to us as 150 as the mass. Let's just go ahead and convert that to a force right away. So we'll multiply by 9.8. You do want to put things in terms of forces. So I'm just going to label that here, 1470. Now conceptually, conceptually, back in the day when we did this problem, we would have just simply said, oh, this guy is going to lift with half, and this guy is going to lift with half. 750 or 735 and 735, right? But we know who's going to have to lift with more. The guy on the left, right? Because it's shifted towards his side, so he's going to have to use more force. So the other force we have, this guy would lift up, right? We can call this, let's call it F left. This guy is going to push up. Let's call this F right. So this would be my FBD, including their locations. Alright, and then we're just going to start doing our summations. And which summations you do, the order doesn't really matter. Honestly, I would recommend doing the torque summation first, because you can choose an axis of rotation that will cancel out one of your forces. So even though you might have, like in this case we have 2 unknowns, if we place our axis of rotation here or here, we can cancel out that force because the distance would be 0, so we would already cancel it out. So it doesn't matter, you could choose here, you could choose here, you could even choose the middle, but that would make it harder. Let's just choose one of these. So let's just choose the one on the left. So when we sum up our torques, torque summation, and I like to just make the equalities. So right here, again, this force on the left gets canceled out. We have this one here, which is going to produce a clockwise torque, okay, of 1470 times its distance, which is 1 meter. And then this guy is going to produce the counterclockwise torque. So we'll set that equal to force of the right side times his distance away, which was 2.5. So notice by using the torque one first, we actually canceled out this force, so we can find force on the right away. Conceptually, how should it compare to half of this, 14? How should it compare to 735? Should be less, right? The force on the right. So, you know, when you can, try to think about the concepts. What's the answer? All right. So to get the other force, we're going to have to use our summation on, well, there is no x summation, so we have to do our y summation. And this one should be pretty straightforward. Even though, you know, we know they're not going to be half and half, we do know what should their two forces add up to. The weight of the refrigerator, right? They combined, they should add up to the weight of the refrigerator. And that's what we'll do. So the summation in y is going to be, well, FL plus FR minus 1470 should equal 0. Or I'm just going to skip that step and go to should equal 1470. Right? So the sum of their two forces should add up to the total weight of the fridge. Just finish and then you can ask. So FL plus 588 equals our 1470. What is our FL then? Did you say 882? Rhina?
I was wondering why for the net torque for the right side, why did we use 3.5 and not 1.5?
So you want to choose your axis of rotation, and so we're choosing the axis to be the edge here. So all distances should be based on the edge. So here to here, which is 1, and then here to here, which is 2.5.
But if we chose the center of mass, would that still work?
It will still work, yeah. And this will cancel out the 1470. What you'll have to do is balance out this guy's, his would be up clockwise, and this guy's, his would be counterclockwise. And you would use the 1 from him and the 1.5 from him. The problem with that is you will get two unknowns here, and you'll have these two unknowns here, and you can substitute and solve. You can still do it. It's just a little bit more algebra that you need to do. So if possible, try to choose an axis that's going to cancel out a force, and that way you'll be left with just one unknown, and you can solve for that.